Hey, this is Steven from the Green Engineers. Welcome back to my research video series. In today's video, we're going to be talking about this prerequisite video, which I'm going to be teaching you how to analyze the mechanical properties of materials. So I'm going to have this new series where I'm going to be comparing the mechanical property data sheets for differing 3D printing materials, and I'm going to go over the comparison between those different materials. So I'm going to have this prerequisite video where I teach you how to read the mechanical materials properties tables and be able to compare multiple different materials to each other. So after watching this video, you'll be able to do your own research about different materials, or you'll be able to have the knowledge to follow my other videos when I compare different materials to each other. So the basics for material science is the stress-strain graph when you're doing testing of materials. And so you're going to have a graph that looks like this with different points on the graph that signify important parts of the material, or important properties, mechanical properties of the material. So the first thing is the Y is the stress and the X is the strain. So stress is measured in pressure, which is PSI for English or pascals for metric. And if you're not familiar with what units pressure, those are the units for pressure, but pressure's the equation for pressure is force over area, but not necessarily an external force. It's internal force over area. So that's basically the internal force inside of the material, because what we're talking about is the internal stress inside of the material. So internal force over area, that is stress, which again is measured in PSI or pascals. Then we have strain. So strain is a unitless value. Strain is measured in the delta L, or the delta length over original length. So delta L is length final minus length initial. So the change in length over the original length. So delta L, or delta F, delta final, L final minus L initial, so the change in length over the original length. And that will give you a unitless value because that's millimeters over millimeters, so the 2 millimeters cancel out, and it's just a number. And then that number will be a ratio, which would be displayed as a percentage. Alright, so we have, this is known as the elongation, so how much the material is deforming according to what stress. So you have lines like this, so here it takes this much stress to get it to strain this much, right? That's the terminology we're going to be using. Alright, and then what we do is we use a tensile tester or a 3-point Ven Test in order to measure the in order to get the results for this guy. So we're going to put a material, which this is actually an ABS graph, so we're going to put that ABS material into a tensile or 3-point Ven Test, and it will measure how much force it puts on the material and then how much strain results from that force. And so that will look something like this. So this is a tensile tester, so you have this eye-shaped sample, and then you put the top of the eye here, the bottom of the eye there, inside these fixed clamped heads. And then what happens is one clamp will stay fixed, the other one will pull. Tensile is pull, compression is push, so tensile is pull. And then it will pull and deform your sample, and then it will have a load cell to measure how much force is being applied. And it'll also have, an encoder that will read how much it's been pulled, how much distance it's been pulled. And assuming there's no slip in the head, assuming that the part isn't slipping out, this movement this way is the same movement with the piece. So it measures deformation as well as force at the same time, and then plots it on a graph. Or you have the 3-point Ven Test for weaker materials that will pull apart in the tensile and not give consistent readings. That's when you have 3 points of testing or flex, You have a point here, which these are the two supporting pins, and then you have this piece, which is basically a modified version of this with just a pin on it, and it'll push down on the material. So it's basically this horizontal, and then you have a piece that comes down this way and pushes on that guy. And then this will bow with compression in the top and tension in the bottom, and then it'll do the same thing. It'll measure how far it's moved this way as your deformation, and also how much force it's putting down. And then that will render, both of those options will render you a graph that looks something like this. Now, this graph, there are two different sections to this graph. There's the ductile section, which is this section here, and then there's the elastic region. So this is the elastic region, and then this is the plastic region. So let's start off, and then those two regions are separated by the yield point, which is this red point right here. So first off, the elastic region is a special region. It's our most important region that we usually use when we design materials, because when we design machines and we pick which material we're going to use for that machine, we're looking mainly at the elastic region. So the elastic region is special because when you're here, and you see it's symbolized mostly by a linear line with a small curve before the yield point. And what happens is when you apply a certain stress, like let's just say we're up here, this is the stress we're doing, like 30 megapascals or whatever. And then so you're bending your material, right? And then you remove that stress, the material will actually snap back to its original shape. It'll fall back down this line and go back to 0, 0. So its original shape. So the same thing like in real life where you're bending a rubber, you're pulling on a rubber band, you let go and it snaps back to its original shape. Or you take a 3D part like an ABS part and you're bending it, and it bends a lot, and you let go, it returns back to its original shape. A long piece of acrylic, you're bending it, whoa, look at how bowed it is, and then you let go and it returns back to its original shape. Or so that is basically what the elastic region is. So that's the important region because we don't want our machines to lose their original shape. So you load it, and then it unloads itself after you remove the load, and it goes back to its original shape. Then we have the plastic region. So the plastic region is the opposite of the elastic region. When we're loading the material and we let go, it maintains that shape. So if you have a 3D printed part and you're bending it, you bend it, you put so much force that now when you let go, it still has that shape. Right? And the main thing that I explain it with is, imagine you have a piece of putty, right? A piece of silly putty or whatever, and it's sitting on your desk, and just sitting on your desk, even though there's forces on it from the atmosphere, it doesn't deform. But when you put your hand around it and then you start to crush it, it'll start to form to your fingers around your hands and put grooves from your fingers around the putty. Now, when you put the grooves around the putty, it will no longer pop back to its original shape. It now has that deformed shape with the ridges from your fingers in it. That is called plastic deformation. And this, we usually don't design our parts or our machines around the plastic deformation region, because you can imagine having like a CNC machine, a manual mill, or a manual lathe, and then like you're machining a piece of steel, and then all of a sudden a piece of it bends, and now you're no longer square anymore. You're no longer trammed. So now every time you're turning or edging or facing a piece of material, now it's doing some sort of weird, not going square, it's doing something weird. So you could imagine having a 3D printer with a gantry that's moving very quickly, and all of a sudden one time it stops very quickly, and then it tweaks out your whole frame. Like your whole frame just like bends everywhere, and then now it's useless as a 3D printer. So we don't want stuff to bend, right? We generally want to load something and it pops back. So you can imagine if we had a bridge with cars going over it, and then one time too big of a car went over it and it bent, and then now there's a big sag in the bridge. That's not what we want. We want it to have the car go over, and then as the car goes off the other end of the bridge, it snaps back to its original shape. That's what we want. Load, go back, load, go back, load, go back. And that's the basics of a machine, is for it to maintain its original shape. All right, and then now there's a different points on this graph that are associated to these different regions, and those points have metrics or numbers applied to them, numbers and units applied to them, and by those numbers and units we could compare different materials to each other, apples to apples. All right, so the first point that we're going to look at is the Young's modulus, which is this guy, the E, or Young's modulus, or flexural modulus. And this guy is actually the slope of this line. So this is estimated to be a linear line here, and the Young's modulus is the slope of that line. So this basically means that this is the measurement of how stiff the material is. So how much stress does it take to give a certain strain? So again, this is equation of y equals this number, y equals EX. So how much stress do I need applied to get it to strain a certain amount, right? So if we had a material that was going right up through the middle here, and so that means that the slope is double, that means it takes twice as much stress to get it to strain the same amount. So twice as much stress to get it to strain the same amount. So that would mean that the material is twice as stiff. While if you had a line that was like this, and it was half, it means it takes half as much stress to get it to strain the same amount. So it's half as stiff. And that's the Young's modulus, flexural modulus, or E, right? Then we have the next point on the graph, which is the yield point. Again, the yield point is the point that's in between the elastic region and the plastic region. So very important, because you don't want to go, generally when you're designing, you do not want to go past the yield point, right? You want to stay to the left in the elastic region of the yield point. So generally this is the most amount of stress you want to put on a material. Okay, so that the yield strength is the maximum amount of stress you could put on a material before it plastically deforms. And you see here, assume perfectly plastic at 43 megapascals. But at 44 megapascals, it's plastic. So 43.2 megapascals is the most amount of pressure or stress we could put on the material before we lose our shape. So we want to do 42, 41, 40, 39, 38, something like that. So we want to stay in this region. So the yield point, this is the maximum amount of stress we could put before we go into plastic deformation. And then here we have the elongation at yield. So how much strain can we go before the material loses its shape, becomes plastically deformed? 3.4%, so that means that if we had this material would deform an extra 3.4% of its original length before it maintains that shape. So again, if we went this line and went straight down, it would say 0.034 right here. So you multiply that by 100, you get 3.4. So this is important, and this is also important because we want to stay below these. So I don't want to distort my material past 3.4%, and I don't want to strain my material past 3.4%, and I don't want to stress my material more than 43.2 megapascals, because otherwise I'll plastically deform. Then we have the other big one, which is the strain to failure. So this is the maximum amount of strain that we could give the material before it breaks at this breaking point right here. So we could load the material, we could stretch the material an additional 25% of its original length. So like 125% of its original length, or additional 25% of its original length before it breaks, which is that's a significant length. So if we take this piece and we take a quarter of it, like here, we could take this quarter and put it on top, and it will still still snap back to its original shape. So that's a lot of elasticity. And then according to this result, we could make the assumption that it is a brittle or a ductile material. A brittle material means that it has a low percentage strain to failure, and ductile material means it has a high percentage of strain to failure. So I usually make the cutter around if it's lower than 10% or like 6%, if it's 6%, 6 or lower, and then sometimes in between 10%, it's a brittle material, and then it's above 10%, it is a pretty ductile material. So this is ABS is a very ductile material, right? And then finally we have the ultimate tensile strength. In this material, it is a lower stress than the yield, but in steel, where the graph goes like this, and then comes down, and then goes back up, quite a bit higher than its first point when it goes into plastic deformation, then that's a significant point, because that is actually your UTS, your ultimate tensile strength. All right, so again, let's go over a quick summary. So elastic region, plastic region, yield point, the stress it takes to get to the yield point, and the strain or percent of elongation it takes to get to the yield point. Then we have the slope of the line, which is Young's modulus or flexural modulus, how stiff the material is. So how much stress versus strain does it take? How much stress does it take to get a certain amount of strain? And then this guy only applies to the elastic region here, because the elastic region is the only region that is linear. This is not linear, right? Then we have the strain to failure. What is the maximum amount of strain that the material will go through? How much stretch will the material go through before breaking? And then the UTS is the tensile stress right before breaking, or in other materials, it is the maximum, the maximum tensile stress. So like steel, the steel would be like up here, and the yield would be down here, right? Yeah, that's pretty much it. So now with this knowledge, you'll be able to compare other materials, 3D printing materials, or other metals, ceramics, blah, 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 to each other. And also you'll be able to follow along with my later videos in this series. Alright guys, I'd like to thank you guys for watching. If you like this video, please subscribe for more videos like it in this series and other series as well. And I'll see you guys in the following videos of the mechanical properties comparing 3D printing materials to each other. Alright, thank you guys for watching. Take it easy.